Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss approximating solutions to ordinary differential equations. So in this topic, we will describe what's going to be covered in the lectures of this subtopic, specifically approximating solutions to ordinary differential equations. We'll introduce and discuss some of the terminology. We will describe the application and use of the implicit function theorem. We will then describe the constraints necessary to find a solution to an ordinary differential equation, and then we will describe the topics in the upcoming lectures and subsections. Now, an ordinary differential equation, as you know from your calculus course, is any equation involving an algebraic expression in a variable, say t, an unknown function y of t, and one or more of its derivatives. The order of an ODE is the highest derivative within the equation. Now, this can include some very bizarre things, such as the function itself plus its derivative plus sine of the function plus cos of the derivative, all squared equaling 1. However, finding a solution to this may be difficult. We instead are going to focus on ODEs that can be usually written in the form y prime is some function of t and y. The second derivative is equal to some function of t, y, and its derivative, and so on and so forth. Essentially, the highest derivative of the function is written in terms, or described in terms of, the variable, the function itself, and any lower derivatives. We will also be looking at approximating solutions to systems of n ordinary differential equations. So this is a situation where we have n equations where each is an equation in the independent variable t, n unknown functions y1 through yn, for example, and at least one derivative of each. So one such example of a system of two ordinary differential equations in two unknown functions are the Lotka-Volterra equations. Here the first function is a product of a known coefficient alpha times the first function minus beta, which is known, times a product of the two functions. The derivative of the second function is negative gamma, again a known constant, times the second unknown function plus delta times the product of the two functions. Now, of course, to get a solution, we must know all four values, alpha, beta, gamma, and delta. Now, interestingly enough, these two differential equations model both autocatalytic chemical reactions and predator-prey relations. Now, in the last slide, the Lotka-Volterra equations are also written in the form the highest derivative is some function of lower derivatives of the functions in question. What allows us to do this? Well, this is something called the implicit function theorem, and something that's way beyond the scope of this course, but we'll state it anyway so that you can be aware why we are using it and why we can do this. The theorem says that if we have any equation of the form where we have a left-hand side that is an expression in n plus 1 unknowns equated to 0, that can usually, not always, but usually be written in the form of one of those variables being equal to a function of the balance of the variables. For example, here we have a differential equation, t squared plus the function squared plus its derivative squared minus 1 is equal to 0. We can write that locally as the derivative is equal to plus or minus the square root of that expression. That should be reasonably obvious. That's just first year, or that's even high school algebra. However, point being, this can be done more generally, and therefore we can always assume when we are analyzing a system, that we can ultimately write down our ordinary differential equation in terms of the highest derivative being a function of the independent variable t, the function itself, and all lower derivatives. Now, recall that in order to find an interpolating polynomial of degree n, we required n plus 1 constraints, one for each of the coefficients in that polynomial. Well, suppose we have an nth order differential equation. To find that function, we're going to have to integrate n times. Each antiderivative is going to introduce one more unknown constant, which we must constrain. So, for example, here's a simple differential equation. The third derivative is equal to cos of t. Well, if that's the case, then the second derivative is sine of t plus an unknown coefficient, a coefficient of constant of integration. Integrate again, we now introduce a second constant of integration, and when we finally integrate a third time, we get a third constant of integration. Therefore, this differential equation is going to require 3 constraints. Thus, an nth order differential equation requires n constraints. Now, one possibility is to describe the state of the system perfectly at one moment in time. So, for example, at time t0, the value of the function is y0, and the value of the derivative is a slope that is initially given. We're going to represent initial constants, often by y0, and initial slopes by y0 with a superscript indicating that it is a derivative. This is called an initial condition because it gives us the state of the system at time t0, and we're going to try to determine what happens to the system for values of t greater than t0. What happens to the system as time advances? Another possibility is to describe the value of the function at different positions. So, for example, suppose the unknown function is some function u, and we have specified that u at some point a is equal to u sub a, and u at another value b is some other constrained value. These are called boundary conditions because they give the state of the system at the boundary of an interval, specifically the interval from a to b. So in this first subsection, we're going to look at approximating solutions to first initial value problems and then boundary value problems. So following this topic, you now have reviewed concepts from your course in calculus. You understand the definition of an ordinary differential equation. You're aware of the implicit function theorem that allows us to write the equation in terms of the highest derivative being equated to some expression or function in the independent variable, the function and its lower derivatives. You've considered the number of constraints that is necessary, and you understand that these constraints can be classified either as being initial values or boundary values. And these will be the two classifications or classes of ordinary differential equations that we will try to solve in the next two subtopics. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!